For almost a century, the story of the universe seemed settled. In the early 1920s, astronomers first realized that the distant galaxies were not drifting randomly through space, but steadily moving away from one another. The discovery came quietly at first, hidden in faint spectral lines measured through fragile glass plates, yet the implication was enormous. The universe was expanding. Space itself was stretching, carrying galaxies with it like distant lanterns floating across an ever-widening sea. From that simple observation emerged one of the most powerful scientific ideas ever proposed. If the universe is expanding today, then in the distant past it must have been smaller. Follow the expansion backwards far enough, and the entire cosmos appears to converge toward a state of extreme density and temperature. A moment when everything that exists today, every galaxy, every atom, every photon of light, was compressed into an unimaginably small and energetic beginning. This idea became known as the Big Bang. For decades, the model proved remarkably successful. It explained why galaxies appear to rush away from us in every direction. It predicted the faint afterglow of ancient radiation that still fills the sky today, the cosmic microwave background discovered accidentally in the 1960s. It described how the first atoms formed when the universe cooled, and how gravity gradually gathered matter into stars and galaxies. Piece by piece, the theory matured into the standard model of cosmology, a framework so powerful that many scientists began to speak of the early universe with surprising confidence. Yet even the most elegant theory remains only as strong as the observations that support it. Astronomy has always advanced through better eyes. Every generation of telescopes has revealed a deeper and more detailed universe. When the first optical observatories mapped the heavens, they saw only nearby stars. Larger telescopes uncovered distant galaxies. Radio observatories exposed violent cosmic jets and invisible clouds of gas. The Hubble Space Telescope, launched in 1990, allowed astronomers to peer billions of years into the past. Its images showed that galaxies existed when the universe was only a fraction of its current age. These discoveries reinforced the idea that the cosmos evolved gradually, growing more complex over time. But Hubble also hinted at mysteries. In its deepest exposures, the telescope captured tiny smudges of light that represented galaxies from the earliest eras of cosmic history. These objects appeared when the universe was only a few 100 million years old. According to the standard model, this was roughly the period when the first stars ignited and primitive galaxies began to assemble. Small structures were expected to form first, slowly merging into the massive galaxies we see today. The early universe, in theory, should have been relatively simple. The reason lies in how cosmic structure forms. In the Big Bang framework, the newborn universe was nearly uniform, filled with hot plasma and faint density fluctuations. Over time, gravity amplified these small irregularities. Regions slightly denser than their surroundings attracted more matter, gradually collapsing into clouds of gas. These clouds cooled and ignited the first generation of stars. Later, those stars gathered into small galaxies, which collided and merged into larger systems. Cosmic history, in this picture, unfolds as a long process of gradual construction, a slow climb from simplicity toward complexity. This expectation shaped the predictions astronomers made about the distant universe. When looking far back in time, the earliest galaxies should appear small, irregular, and relatively faint. Their stars would still be forming, their structures still chaotic. The massive spiral galaxies and enormous elliptical systems seen in the modern universe should not yet exist. There simply would not have been enough time for gravity to build them. For years, the available observations roughly matched this expectation. Hubble saw many distant galaxies that appeared young and irregular, just as theory predicted. But its ability to probe the earliest epochs was limited by a simple physical barrier. Light from extremely distant galaxies is stretched by cosmic expansion, shifting toward longer wavelengths. By the time the most ancient light reaches Earth, it has moved out of the visible spectrum and into the infrared. Hubble was not designed to see that far. Astronomers knew that the real frontier of cosmic history lay hidden in these stretched wavelengths. To study the first galaxies properly, a telescope would need to operate primarily in the infrared, with a mirror large enough to gather the faintest signals from the edge of the observable universe. It would also need to sit far from Earth, shielded from heat and stray light, cooled to temperatures colder than most natural environments in the solar system. Such a telescope would be an engineering challenge unlike anything attempted before. For more than 2 decades, scientists and engineers worked toward that goal. The project endured redesigns, technical crises, and years of delay. At times, its future seemed uncertain, its cost controversial, its launch date repeatedly postponed. Yet the promise remained extraordinary. If successful, the new observatory would look deeper into cosmic time than any instrument in history. It would observe the first galaxies, the first stars, perhaps even the first light that emerged after the universe cooled from its earliest chaos. Eventually, the telescope was ready. On a clear morning in late December of 2021, a rocket lifted from the coast of French Guiana, carrying one of the most complex scientific instruments ever built. Folded inside the rocket's fairing was a golden segmented mirror and a vast sun shield the size of a tennis court. Over the following weeks, the observatory unfolded itself in deep space with delicate precision. Each deployment a moment of tense anticipation for the engineers who had spent years preparing the mission. The telescope was named after James Webb, a former administrator of the American Space Agency during the early years of lunar exploration. Its mirror, more than 6 meters across, would collect more light than any space telescope before it. Its instruments were designed to detect the faint infrared glow of objects formed near the dawn of cosmic history. When the first images arrived, they stunned even the astronomers who had planned the mission. The telescope quickly began revealing galaxies so distant that their light had traveled for more than 13 billion years before reaching Earth. These galaxies appeared when the universe was less than 1 billion years old, some even earlier. That alone would have been remarkable, but what truly surprised scientists was not simply their existence. It was their appearance. Instead of small, chaotic structures, many of the newly observed galaxies looked unexpectedly mature. Some appeared massive, containing enormous quantities of stars. Others displayed shapes that seemed far more organized than anticipated for such an early era of cosmic history. In several cases, the brightness of these galaxies suggested star populations far larger than models predicted could exist so soon after the Big Bang. The universe, it seemed, may have built its first galaxies far more quickly than expected. At first, astronomers approached the results cautiously. Early observations often contain uncertainties. Distances can be misinterpreted, faint objects misidentified, subtle measurement errors amplified by excitement. Yet as more data arrived, the pattern became harder to ignore. The telescope was consistently revealing galaxies that appeared too large, too luminous, and too developed for the age of the universe in which they were seen. Some researchers began to ask a quiet but profound question. What if the early universe was not quite as simple as the standard model had assumed? This question does not mean the Big Bang itself is necessarily wrong. The expanding universe, the cosmic microwave background, and many other observations still support the idea of a hot, early beginning. But cosmology is a layered science. Even when the overall framework is correct, the details of how structure forms can still contain surprises. The rate at which galaxies grow, the processes that ignite early star formation, the role of dark matter and invisible physics in shaping cosmic history. all of these factors remain active areas of investigation. The new telescope had opened a deeper window into that mystery. For the first time, astronomers could observe the universe during its earliest chapters with extraordinary clarity. Every faint galaxy detected in those deep fields carried information from an age when the cosmos was only a few % of its current age. Each observation offered a glimpse of how quickly the universe transformed from a nearly uniform sea of primordial gas into a landscape filled with stars, galaxies, and complex cosmic structures. Yet the deeper the telescope looked, the more intriguing the story became. Because hidden within those ancient photons may be clues that challenge long-held assumptions about how the universe evolved, and perhaps even about how the Big Bang itself unfolded in its earliest moments. And as the data continued to arrive, one possibility began to emerge slowly among astronomers studying the new observations. The first galaxies may not have been small, fragile structures at all. They may have appeared suddenly, rapidly assembling vast numbers of stars in a surprisingly short span of cosmic time, leaving modern scientists to reconsider just how quickly the young universe learned to build structures we see today. If the earliest galaxies truly formed faster than expected, then something within the young universe must have accelerated the process of cosmic construction. The question is not whether galaxies existed early. Astronomers have known for decades that they did. The real puzzle is how such enormous structures could appear so quickly after the beginning of cosmic time. To understand why this is surprising, it helps to imagine the conditions of the universe shortly after the Big Bang. At that time, the cosmos was still extremely hot and filled with a glowing mixture of particles and radiation. Protons, electrons, and light constantly collided within a dense plasma that filled all of space. Photons scattered so frequently that the universe was effectively opaque. Light could not travel freely because every attempt to move across space resulted in another collision with charged particles. This state lasted for hundreds of thousands of years. Eventually, the universe cooled enough for electrons to combine with protons, forming the first stable atoms of hydrogen. When this happened, the fog of plasma suddenly cleared. Light could finally travel across space without constant interference. The radiation released at that moment still exists today as the cosmic microwave background, a faint glow that fills the entire sky and provides one of the strongest pieces of evidence for the Big Bang model. After this transition, the universe entered what astronomers often call the cosmic dark ages. There were still no stars, no galaxies, and no sources of light except the fading radiation left over from the early universe. Space was filled with neutral hydrogen gas and invisible clumps of dark matter slowly gathering under the influence of gravity. Tiny density variations, seeded in the earliest moments of cosmic expansion, began to grow. Regions with slightly more matter attracted additional material, gradually forming the first gravitational wells where gas could accumulate. According to traditional models, this process should have taken time. Gravity is powerful but not instantaneous. Gas clouds must cool before they can collapse into stars. Turbulence must settle. Angular momentum must dissipate. Each stage introduces delays in the process of star formation. The earliest galaxies, therefore, were expected to be modest structures, small clusters of stars gradually assembling into larger systems through collisions and mergers. But the James Webb Telescope has revealed objects that appear far more massive than these early models predicted. In several deep observations, astronomers identified galaxies whose brightness suggests enormous numbers of stars already existed within them. Some of these galaxies may contain tens of billions of stars, numbers comparable to large modern galaxies. If these measurements are confirmed, it would mean that within only a few 100 million years after the Big Bang, the universe had already constructed systems approaching the scale of the Milky Way. That is an astonishing possibility. To put the timeline into perspective, the Milky Way itself required billions of years to reach its present size. Our galaxy formed through countless mergers with smaller systems, absorbing stars and gas from neighboring galaxies over vast stretches of cosmic time. Yet the galaxies now detected by the James Webb Telescope appear to have achieved similar masses far earlier in the history of the universe. Such rapid growth challenges many assumptions about early cosmic evolution. Some astronomers propose that the first stars may have been dramatically larger than those forming today. Massive primordial stars would burn intensely and live short lives, producing heavy elements and triggering additional waves of star formation. If these stars formed in enormous clusters, they could quickly illuminate young galaxies with tremendous brightness, making them appear more developed than they truly are. Another possibility involves the mysterious substance known as dark matter. Dark matter does not emit light, yet it dominates the gravitational structure of the universe. Galaxies form within vast halos of this invisible material. If dark matter clumped more efficiently in the early universe than models suggest, it might have created deep gravitational wells capable of gathering gas rapidly. In such environments, star formation could ignite earlier and proceed more quickly than predicted. Yet even these explanations may not fully account for the observations. Some of the galaxies detected by the telescope appear not only massive, but also surprisingly organized. Their shapes hint at disks or compact structures that normally require long periods of dynamical evolution to develop. If confirmed, this would suggest that the processes shaping galaxies were already operating with remarkable efficiency when the universe was still extremely young. This raises a deeper question about the conditions present during the first few 100 million years of cosmic history. Perhaps the early universe was not simply a slower version of the modern cosmos, but an environment governed by more extreme physical processes. Gas clouds may have collapsed under intense pressure. Radiation from the first stars may have triggered rapid cycles of heating and cooling. Interactions between dark matter and ordinary matter may have behaved differently in those primordial conditions. In other words, the early universe may have been far more dynamic than previously imagined. The James Webb Telescope is uniquely suited to investigate these possibilities because it observes infrared light with extraordinary sensitivity. Light from the earliest galaxies has been stretched by cosmic expansion until its wavelengths are far longer than those visible to human eyes. Webb's instruments can capture these faint signals and separate them into detailed spectra, revealing the chemical composition, temperature, and motion of distant objects. Through this technique, astronomers can determine how old a galaxy is and how quickly its stars formed. The first spectroscopic measurements from Webb have already begun to confirm that many of the observed galaxies truly lie at extreme distances. Their light originates from an era when the universe was less than 1 billion years old. Each spectrum acts like a time capsule, preserving information about the physical conditions that existed when those galaxies first began shining. These results suggest that the earliest phases of cosmic history may have unfolded more rapidly than theoretical models predicted. If galaxies formed sooner and grew larger than expected, then the processes driving cosmic evolution must be reconsidered. Theories describing how gas cools, how stars ignite, and how gravitational structures assemble may need refinement. The standard cosmological model may remain broadly correct, but its timeline could require adjustment. For scientists, this is not a crisis, but an opportunity. Cosmology advances precisely through moments like these, when new observations reveal phenomena that existing theories struggle to explain. Each discrepancy invites deeper investigation. Perhaps improved simulations will show that early star formation naturally produces brighter galaxies than previously assumed. Perhaps the first generations of stars behaved differently from anything observed in the modern universe. Or perhaps the telescope has uncovered hints of physics not yet fully understood. Some researchers have even speculated that the earliest galaxies might host massive black holes that formed surprisingly early. If enormous black holes existed shortly after the first stars, they could influence surrounding gas, triggering intense bursts of star formation and shaping the structure of young galaxies. Evidence for such early black holes has already appeared in several observations of distant quasars, suggesting that extreme gravitational objects were present when the universe was still very young. These possibilities remain under active study. Astronomers are carefully examining every new dataset from the James Webb Telescope, searching for patterns that might reveal how the earliest galaxies formed. Each observation refines the cosmic timeline. Each spectrum provides another clue about the processes unfolding during the universe's first chapters. What is becoming increasingly clear is that the early universe was not a quiet place slowly assembling its first structures. Instead, it may have been a remarkably active environment where gravity, radiation, and primordial gas interacted with extraordinary intensity, building galaxies far faster than scientists once imagined. The possibility that galaxies formed earlier and grew faster than expected forces astronomers to re-examine how the first structures emerged from the young universe. The traditional model describes a slow hierarchy of formation. Small clouds of gas collapse first, producing the earliest stars. These stars gather into tiny protogalaxies. Over millions of years, those systems merge and accumulate additional matter, eventually forming the large spiral and elliptical galaxies observed today. This framework is known as hierarchical structure formation. Within it, cosmic evolution resembles a long process of assembly. Gravity pulls matter together piece by piece. Small objects appear first, then combine to form larger ones. Simulations based on this idea have successfully reproduced many features of the modern universe, including the distribution of galaxies and the large-scale filaments of matter that stretch across billions of light-years. But the new observations from the James Webb Telescope hint that the earliest phases of this process may have unfolded with unexpected speed. One reason lies in the behavior of primordial gas. In the early universe, the chemical composition of matter was extremely simple. Hydrogen and helium dominated almost completely, with virtually no heavier elements. Modern stars form in clouds enriched with elements such as carbon, oxygen, and silicon, which help gas radiate heat and collapse efficiently. In contrast, primordial gas lacked many of these cooling pathways. At first glance, that should have slowed star formation. Yet theoretical work suggests another possibility. Without heavier elements, the first stars may have formed under very different physical conditions. Gas clouds could collapse into extremely massive stellar objects, some hundreds of times larger than the Sun. These enormous stars would burn intensely and live only brief lives before exploding as powerful supernovae. In doing so, they would rapidly enrich their surroundings with heavier elements, transforming the chemical environment of early galaxies. Such explosions could trigger rapid waves of additional star formation. The energy released by massive primordial stars would compress nearby gas clouds, igniting new generations of stars in a chain reaction of cosmic construction. Within a relatively short span of time, a region of space could transform from a dark cloud of hydrogen into a luminous young galaxy containing millions or billions of stars. If this process occurred efficiently across many regions of the early universe, galaxies could indeed grow far faster than traditional models predicted. Another factor involves the distribution of dark matter. Although invisible, dark matter forms the gravitational scaffolding upon which galaxies are built. Vast halos of this mysterious substance surround galaxies and extend far beyond the visible stars within them. These halos act like cosmic traps, capturing gas that eventually forms stars. In the earliest epochs, the universe was denser than it is today. matter existed in closer proximity, and gravitational interactions could proceed more rapidly. Dark matter halos forming during this period might have collapsed quickly, creating deep gravitational wells capable of drawing in enormous quantities of gas. Once gas began falling into these wells, star formation could accelerate dramatically. Computer simulations exploring these scenarios have produced intriguing results. When conditions resembling the early universe are modeled with sufficient resolution, galaxies sometimes appear sooner and grow faster than earlier calculations suggested. The interplay between dark matter collapse, gas cooling, and intense radiation from the first stars can produce bursts of rapid growth that resemble some of the objects now observed by the James Webb Telescope. Yet even these simulations struggle to reproduce the most massive galaxies seen at extreme distances. The brightness of several newly discovered objects implies stellar populations that may exceed what current models can comfortably explain. If their estimated masses are confirmed, then astronomers must ask whether some additional mechanism contributed to their formation. One candidate involves the early creation of supermassive black holes. In the modern universe, nearly every large galaxy appears to host a black hole at its center. The black hole in the Milky Way contains millions of times the mass of the Sun. In some galaxies, these objects grow to billions of solar masses and become the engines of quasars, luminous beacons visible across immense cosmic distances. Observations have already revealed quasars existing less than 1 billion years after the Big Bang. The existence of such massive black holes so early in cosmic history remains one of the enduring puzzles of astrophysics. If black holes began forming extremely early, they could influence the growth of surrounding galaxies. A rapidly feeding black hole releases enormous energy into nearby gas. This energy can either suppress star formation by heating the gas or compress it in ways that trigger new stellar activity. The interaction between black holes and young galaxies may therefore shape how quickly stars appear and how rapidly galaxies expand. Recent observations from the James Webb Telescope have begun detecting signs that some distant galaxies may indeed contain active black holes. These objects emit distinctive spectral signatures that reveal intense energy emerging from their centers. If confirmed, such discoveries would indicate that massive gravitational engines were already present during the universe's earliest stages. Their presence could help explain why some galaxies appear unexpectedly bright. Another avenue of investigation concerns the rate of cosmic expansion itself. The speed at which the universe expands determines how quickly matter spreads apart after the Big Bang. If expansion occurred slightly differently than current models assume, it could alter the timeline available for galaxies to grow. Modern cosmology relies heavily on a parameter known as the Hubble constant, which describes the rate of cosmic expansion today. Measurements of this value have produced a curious discrepancy in recent years. Observations based on the cosmic microwave background suggest one expansion rate, while measurements based on nearby galaxies suggest another slightly higher value. This disagreement, often called the Hubble tension, remains unresolved. Some researchers wonder whether the discrepancy hints at missing physics in our understanding of cosmic expansion. If the early universe expanded at a different rate than expected, the formation of galaxies might also have proceeded differently. Even small adjustments to the expansion timeline could influence how quickly gravitational structures assembled. For now, such ideas remain speculative. Astronomers approach these questions cautiously because distance measurements at extreme cosmic scales are challenging. Determining the exact age and mass of distant galaxies requires careful analysis of faint signals. As more data accumulates from the James Webb Telescope, scientists will refine these measurements and determine whether the earliest galaxies truly exceed theoretical expectations. But regardless of the final outcome, the telescope has already achieved something remarkable. It has pushed observational cosmology into an era where the first few 100 million years of cosmic history are no longer hidden behind technological limits. The earliest chapters of the universe are now open to direct study, and with each new observation, the narrative of cosmic evolution becomes richer and more complex. Instead of a simple, gradual progression from darkness to structure, the young universe may reveal itself as a period of astonishing activity, where stars ignited rapidly, galaxies assembled quickly, and the foundations of the modern cosmos emerged far sooner than once imagined. As the first months of observations from the James Webb Telescope turned into years of data, astronomers began approaching the discoveries with increasing precision. Early images had revealed unexpectedly bright galaxies at extreme distances, but brightness alone can sometimes be misleading. A galaxy may appear luminous not because it contains enormous numbers of stars, but because those stars are forming at an unusually intense rate. Distinguishing between these possibilities requires careful analysis of the light arriving from those distant systems. This is where spectroscopy becomes essential. Every element in the universe interacts with light in a unique way. Hydrogen, oxygen, carbon, nitrogen, and other atoms absorb and emit specific wavelengths that act like fingerprints. By splitting the faint light from a distant galaxy into its component wavelengths, astronomers can determine which elements are present and how quickly stars are forming. Spectroscopy also allows scientists to measure the galaxy's redshift, the stretching of light caused by cosmic expansion, which reveals how far away the object truly is. The James Webb Telescope was designed precisely for this task. Its instruments can detect extremely faint infrared signals and separate them with remarkable accuracy. For galaxies whose light began its journey more than 13 billion years ago, this capability is critical. Without infrared sensitivity, these ancient signals would remain invisible to telescopes operating in visible light. When astronomers began collecting spectra from some of the earliest candidate galaxies, the results provided confirmation that many of them truly existed at extraordinary distances. Several objects were identified at redshifts greater than 10, meaning their light began traveling toward Earth when the universe was less than 500 million years old. At that stage, cosmic history was still in its infancy. The first generations of stars had only recently formed, and the intergalactic medium remained partially filled with neutral hydrogen left over from the cosmic dark ages. Yet within this young universe, entire galaxies were already shining. The spectra revealed active star formation occurring at remarkable rates. In some galaxies, hundreds of solar masses worth of new stars appeared to be forming every year. For comparison, the Milky Way today produces only a few solar masses of new stars annually. Such intense activity suggests that young galaxies may have experienced brief but powerful bursts of stellar production, rapidly building their populations in relatively short periods of time. These bursts could explain some of the unexpected brightness detected in early Webb images. If galaxies experienced concentrated periods of star formation, their light output would surge dramatically. A galaxy undergoing such an event might appear far more massive than it actually is. Over time, as the most massive stars burned out and exploded as supernova, the brightness would decline, leaving behind a more moderate stellar population. But even after accounting for these possibilities, several galaxies still appear unusually large. Some objects show evidence of surprisingly mature chemical compositions. The presence of heavier elements suggests that multiple generations of stars have already lived and died within these galaxies. Each stellar generation enriches the surrounding gas with heavier elements through supernova explosions, gradually transforming the chemical makeup of the galaxy. Finding these elements in extremely distant galaxies implies that star formation began even earlier than the observed light suggests. In other words, by the time the telescope captured their glow, these galaxies had already experienced significant cosmic history. Their stars had lived through cycles of birth and death, seeding their environment with heavier elements and allowing subsequent generations of stars to form in increasingly complex conditions. This pushes the origin of the very first stars further back in time. Astronomers refer to this early stellar population as population 3 stars, hypothetical objects composed almost entirely of hydrogen and helium. Because they lacked heavier elements, these stars are thought to have been extraordinarily massive and short-lived. Their lifetimes may have lasted only a few million years before ending in violent explosions. Direct evidence for population 3 stars remains elusive, yet their existence is strongly predicted by theory. If these stars did form in large numbers, they could have transformed the early universe rapidly. Their radiation would ionize surrounding hydrogen gas, gradually clearing the fog that filled intergalactic space. Their supernova explosions would distribute heavier elements across young galaxies, enabling new generations of stars to form with more complex chemistry. This process is known as cosmic reionization. During this epoch, the radiation from early stars and galaxies gradually ionized the neutral hydrogen that filled much of the universe after the cosmic dark ages. As more stars ignited, the surrounding gas became increasingly transparent to ultraviolet light. Eventually, large regions of intergalactic space transitioned from opaque to transparent, allowing light to travel more freely across cosmic distances. The timing of reionization remains one of the key questions in cosmology. Observations from the cosmic microwave background suggest that the process began several 100 million years after the Big Bang and continued for hundreds of millions of years. The galaxies now observed by the James Webb Telescope appear to lie within this critical era. Their intense star formation may have played a major role in driving the transformation of the universe from darkness into transparency. In this sense, the earliest galaxies were not merely passive structures. They actively reshaped the universe around them. Their radiation altered the physical state of intergalactic gas. Their supernova explosions enriched cosmic environments with heavier elements. Their gravitational influence gathered additional matter, fueling further cycles of star formation. These processes gradually produced the complex cosmic web observed today. Across vast scales, galaxies are not distributed randomly, but form long filaments and clusters separated by enormous voids. This structure reflects the underlying distribution of dark matter, whose gravitational pull organizes matter across billions of light-years. The galaxies detected by the James Webb Telescope represent the earliest visible points within that immense network. By studying them, astronomers can trace how the cosmic web began. Each new observation helps refine our understanding of how quickly the first structures formed and how efficiently matter gathered into galaxies. Over time, the growing dataset from Webb will allow scientists to reconstruct a timeline of cosmic evolution with unprecedented detail. Already, the telescope has begun identifying hundreds of candidate galaxies from extremely early epochs. Some appear as faint red points barely distinguishable from background noise. Others reveal more complex shapes, suggesting internal structure and organized star formation. With additional observations, astronomers hope to determine whether these galaxies are isolated systems or part of larger clusters already forming in the young universe. If clusters existed this early, it would suggest that gravitational structure developed rapidly across enormous scales. Such findings would reinforce the emerging picture of a young universe far more dynamic than once imagined. Rather than slowly assembling galaxies over billions of years, cosmic history may have begun with bursts of intense activity, rapidly transforming primordial gas into stars and galaxies within a relatively brief spell of time. The James Webb Telescope is only beginning to explore this epoch. Over the coming years, deeper surveys will reveal even fainter and more distant galaxies. Each discovery will push the observational boundary closer to the moment when the very first stars ignited. Somewhere beyond the current limit lies the transition between the cosmic dark ages and the birth of the first luminous structures. When that boundary is finally observed directly, astronomers may witness the moment when the universe first learned to shine. As astronomers continue examining the earliest galaxies revealed by the James Webb Telescope, the focus has gradually shifted from simple discovery to deeper interpretation. Finding distant galaxies is only the beginning. The real challenge lies in understanding what those galaxies reveal about the physical laws shaping the universe during its earliest stages. Every observation from the telescope adds a new data point to a timeline that stretches back more than 13 billion years. Yet that timeline remains incomplete. The earliest observable galaxies already show signs of complexity, meaning that significant cosmic evolution must have occurred even earlier, in periods still only partially visible to modern instruments. This realization pushes scientific curiosity toward the very first moments of structure formation. Between the release of the cosmic microwave background and the appearance of the earliest known galaxies lies a period of cosmic history that remains largely hidden. During this time, the universe transitioned from a smooth distribution of matter into the first gravitational structures capable of forming stars. Dark matter halos collapsed. Gas accumulated. The first stellar furnaces ignited, releasing radiation that began transforming the surrounding cosmos. The details of that transformation remain uncertain. One reason is that the earliest stars themselves may have been very different from the stars seen today. Without heavy elements to assist in cooling gas clouds, primordial star formation likely produced extremely massive objects. Some theoretical models suggest stars hundreds of times the mass of the Sun. These giants would burn rapidly, emitting enormous quantities of radiation before ending their lives in powerful explosions. Such explosions would have dramatic consequences for the surrounding environment. When massive stars die as supernova, they eject heavy elements into space at tremendous velocities. These elements mix with surrounding gas, altering the chemistry of future star-forming regions. Over time, this enrichment process transforms galaxies from simple hydrogen and helium systems into complex chemical ecosystems capable of producing planets and eventually life. The earliest galaxies therefore served as the universe's first chemical laboratories. Within them, the elements required for rocky planets, oceans, and biological molecules began to emerge through cycles of stellar birth and death. The galaxies observed by the James Webb Telescope represent the earliest known environments where this transformation may have begun. Understanding how quickly those cycles unfolded is crucial. If heavy elements appeared earlier than expected, it suggests that stellar evolution in the young universe progressed at remarkable speed. Multiple generations of stars may have lived and died within a relatively short span of cosmic time, rapidly enriching galaxies with the materials required for later cosmic complexity. These insights also connect to one of the most profound questions in astrophysics. How quickly did the universe become capable of supporting planetary systems similar to our own? Time formation requires elements such as carbon, oxygen, silicon, and iron, all produced within stars. The presence of these elements in very early galaxies suggests that the ingredients for planets may have appeared far sooner than once believed. In principle, planetary systems could have begun forming within the first billion years of cosmic history. While the existence of such early planets remained speculative, the chemical evidence uncovered by the telescope suggests that the raw materials were present. At the same time, the growing catalogue of early galaxies is helping astronomers refine models describing how the universe expanded and evolved. Observations of distant galaxies allow scientists to measure how the rate of cosmic expansion has changed over time. These measurements contribute to ongoing efforts to understand dark energy, the mysterious force driving the accelerated expansion of the universe. Although dark energy dominates the universe today, its influence during the earliest epochs was far weaker. In the young cosmos, gravity played the dominant role in shaping structure. Matter clumped together, forming the first stars and galaxies. Only later did dark energy begin to influence the large-scale evolution of the universe, gradually accelerating the expansion of space. Studying early galaxies therefore offers a way to observe the universe during a period when gravity controlled cosmic dynamics almost entirely. This allows astronomers to test whether theoretical models describing dark matter and gravitational collapse accurately reproduce the structures now observed by Webb. If discrepancies appear, they may reveal new physics operating within the invisible components of the universe. Already, some researchers are considering whether subtle modifications to existing cosmological models may be required. Perhaps the properties of dark matter differ slightly from what current theories assume. Perhaps early star formation operated under conditions that produced unusually efficient bursts of stellar growth. Or perhaps certain observational interpretations will be revised, as additional measurements refine the distances and masses of the galaxies involved. Science progresses through this cycle of observation and revision. New data challenges existing models. Theories evolve to incorporate the discoveries. Future observations then test the updated predictions. The James Webb Telescope has accelerated this process dramatically by opening a region of cosmic history that was previously inaccessible. The telescope is expected to operate for many years, continuously gathering deeper observations of the early universe. Large survey programs are already underway, mapping thousands of distant galaxies and measuring their properties with increasing precision. Each new dataset will improve estimates of galaxy ages, masses, chemical compositions, and star formation rates. Over time, these measurements will allow astronomers to reconstruct the earliest phases of cosmic history with unprecedented clarity. The ultimate goal is to understand how the universe transitioned from a nearly uniform sea of particles into the intricate cosmic web visible today. That transformation required the formation of the first stars, the assembly of the first galaxies, and the gradual emergence of large-scale structures across billions of light-years. The galaxies now being discovered represent the earliest visible steps in that enormous process. They show that the universe began constructing complex structures far earlier than many scientists once imagined. Within only a few 100 million years after the Big Bang, regions of space were already blazing with star formation, producing galaxies whose light would travel across cosmic time to reach modern telescopes. Yet despite these advances, the deepest questions about the origin of the universe remain open. What triggered the initial fluctuations that later grew into galaxies? How did the first stars ignite within primordial gas? What role did dark matter play in guiding the formation of cosmic structures? And how did the earliest galaxies evolve into the vast populations observed across the modern universe? Each observation from the James Webb Telescope brings astronomers closer to answering these questions. By peering deeper into space, the telescope effectively looks further back in time, allowing scientists to witness the universe during its earliest stages of development. Every faint galaxy discovered in those distant fields represents a message from the past, carrying information about conditions that existed billions of years before Earth formed. Through these ancient signals, the universe gradually reveals its history. What once appeared as a simple narrative of gradual cosmic evolution is becoming a richer and more dynamic story. The young universe may have been a place of rapid transformation, where gravity, radiation, and primordial matter interacted with extraordinary intensity to produce the first luminous structures. And as the James Webb Telescope continues its exploration, the earliest chapters of that story are finally coming into view. Even with the extraordinary power of the James Webb Telescope, there is still a boundary beyond which observation becomes increasingly difficult. Light from the earliest structures must travel across more than 13 billion years of cosmic expansion before reaching Earth. Along the way, its wavelength stretches dramatically, its intensity fades, and the signals arriving at modern instruments become extraordinarily faint. Yet each faint photon carries information from a time when the universe itself was still taking shape. The galaxies currently being observed represent only the visible portion of a much larger process unfolding across the young cosmos. Behind them lies an earlier era when the first stars ignited in isolated pockets of collapsing gas. These stars illuminated regions of darkness that had persisted since the universe cooled enough for atoms to form. The moment when the very first stars appeared is sometimes called cosmic dawn. It marks the transition from a universe filled with darkness to one where light once again began spreading through space. For hundreds of millions of years after the Big Bang, there were no stars at all, only clouds of hydrogen and helium drifting through expanding space. Gravity slowly gathered that gas into denser regions until the pressure at their centers became high enough to ignite nuclear fusion. When fusion began, the universe experienced its first true sources of starlight. These earliest stars likely formed in relative isolation, scattered across enormous distances. Their intense radiation began altering the surrounding intergalactic medium. Ultraviolet light stripped electrons from neutral hydrogen, gradually creating expanding bubbles of ionized gas. As more stars formed, these bubbles grew larger and began overlapping, eventually transforming the entire universe into a transparent environment through which light could travel freely. The galaxies now being discovered by the James Webb Telescope emerged within this transforming landscape. Their stars contributed to the radiation that reshaped intergalactic space. Their gravity gathered additional matter, fueling new waves of star formation. Over time, these systems would collide, merge, and evolve into larger galaxies resembling those seen in the nearby universe. Yet the most distant galaxies detected so far may not represent the very first generation of galaxies. There may exist even earlier systems too faint for current surveys to detect clearly. These primordial structures could consist of only a few million stars, barely visible across the vast distances separating them from Earth. Discovering them will require even deeper observations and perhaps future telescopes designed specifically to explore the cosmic dawn. Already astronomers are planning such missions. Concepts for next-generation space observatories are under discussion, with mirrors even larger than the one carried by the James Webb Telescope. These future instruments could detect the faintest glimmers of light produced by the first galaxies, and perhaps even individual clusters of population 3 stars. If such observations become possible, scientists may finally witness the birth of the earliest stellar systems directly. But even without those future instruments, the discoveries made by the James Webb Telescope have already reshaped how astronomers think about the young universe. The early cosmos appears to have been far more productive than many theoretical models suggested. Galaxies assembled quickly. Stars formed in enormous numbers. Chemical complexity emerged rapidly through repeated cycles of stellar evolution. Rather than a slow emergence from simplicity, cosmic history may have begun with intense bursts of activity. Within only a few 100 million years after the Big Bang, the universe was already constructing large stellar systems and transforming primordial matter into the elements required for later cosmic structures. This rapid transformation highlights the remarkable efficiency of gravity and nuclear fusion in shaping the universe. The galaxies observed by Webb are not merely distant objects. They are records of the processes that eventually produced everything that followed. Within their early generations of stars, the elements of carbon, oxygen, silicon, and iron were forged. These elements would later form planets, oceans, atmospheres, and eventually the biological chemistry that makes life possible. In that sense, the study of early galaxies connects directly to the long chain of events that ultimately led to the existence of Earth. The atoms within every living organism were once created inside stars that lived and died billions of years ago. By examining the earliest galaxies, astronomers are effectively tracing the beginning of that cosmic lineage, following the formation of the elements that would later become part of planetary systems and living worlds. This perspective reveals the deeper significance of studying the early universe. Cosmology is not only about understanding distant galaxies. It is about uncovering the sequence of events that transformed a simple universe of hydrogen and helium into one capable of supporting immense complexity. Every observation of the early cosmos reveals another stage in that transformation. The James Webb Telescope has provided the most detailed glimpse yet into this formative era. Its images and spectra allow scientists to examine galaxies whose light began traveling toward Earth when the universe was only a few % of its present age. These ancient signals contain information about star formation, chemical enrichment, gravitational structure, and the expansion of space itself. Piece by piece, those signals are helping astronomers refine the story of cosmic evolution. The emerging picture is one of a universe that began with extraordinary simplicity, but rapidly developed intricate structure. Within relatively short spans of time, gravity gathered matter into galaxies, stars produced heavier elements, and radiation reshaped the surrounding cosmos. The universe was not static during its early history. It was a place of rapid change and dramatic transformation, where immense forces operated across enormous scales. The galaxies now being revealed by modern telescopes offer direct evidence of that dynamic past. And as observations continue, the boundaries of the known universe will continue to expand. New surveys will discover galaxies even farther away, pushing the observational frontier closer to the moment when the first stars ignited. Each new discovery will refine the timeline of cosmic history and deepen our understanding of how the universe evolved. Some questions will inevitably remain open. The precise mechanisms that governed the formation of the first stars, the nature of dark matter, and the deeper origin of cosmic expansion remain among the greatest mysteries in modern science. Yet with each generation of telescopes, humanity gains a clearer view of the universe's earliest chapters. The James Webb Telescope represents one of the most powerful tools ever built to explore those chapters. Through it, astronomers are witnessing the distant glow of galaxies that formed when the universe was still young, revealing how quickly cosmic structure emerged from the aftermath of the Big Bang. And hidden within that ancient light is the story of how the universe first began to build the vast and intricate cosmos that surrounds us today.